Okay, today I'm just gonna have this little video here to talk about flash drums and how we design them. So let me just start out with a typical drum design, typical flash drum design, where we're trying to again separate two or more materials. And we have here our flash drum F, Z, and we also have here two streams, V and Y for the vapor. V is the flow rate of the vapor, Y is the molar concentration, L and X. L is the molar flow rate of the liquid phase, X is the concentration, again Y and X. Z are all the most volatile components of those streams. We're going to be restricting our design or our analysis initially to just two components. So we'll have one component more volatile than the other. So one way to do this is to fix the mass balances, and oftentimes we do this by fixing the ratio of V to F, or how much of the feed comes in and leaves as vapor. And in this case, we solve for X, Y. That's what we would want to solve for. So we can easily use material balances to solve for F, V, and L, but we might not know what X and Y are in the outlet streams. So that's one way we can do this. The other is to fix the separations. In this case, we're fixing X and Y, and also temperature, and we end up solving for the flows. So what are L and V? That's what we would end up solving for. So two different ways, and there are other types of specifications we can also do, but these are two of the most common ones. So let's just look at an example of how we solve this. Solving the flash drum. So we have here two bits of information. One, again, we have our vapor-liquid equilibrium curve right here, and there's my little straight line for my Y equals X line. We have here some flow rate. We might know F is equal to 100 moles per second. Z, which would be the mole concentration of the more volatile component, we'll just call it 0.3. And then we have here two flow rates and two concentrations, so L and X. And we may be given some specification that V over F is equal to 0.3. And we are trying to, we use this information, or eventually would like to solve for V and L, Y and X. Well, the material balances, they're pretty easy, or pretty straightforward. Let me change that there. Straightforward for solving. We can just write, I'll just write this as equation 1, F is equal to L plus V. I'll write equation 2 here, F times Z is equal to L times X. Oh, why did I write Z there? L times X plus V times Y. So those are our two material balances we write out. And then we have this third part here, 3 L over V. I'm just doing all sorts of mistakes here in the writing. V over F is equal to 0.3. And if we just take 1 and 3 and solve it, we're going to get V is equal to 30 mole per second, and L is equal to 70 mole per second. And those are our answers right there for V and L. So again, that's our answers. And now we have to go about figuring out how to sign for X and Y. Just put that right there. So now, what's our strategy going to be for X and Y? Well, we're going to have to use our vapor-liquid equilibrium data. We've used our material balance equations to solve for V and F. And again, we're going to have to rely on this curve here, our XY plot. Looks something like that. We're going to have to rely on that to solve for it, Y and X. And its difficulty is, or part of the difficulty is, this is not a straightforward equation. This is a graphical illustration of the data. So we're going to have to use, we can't just solve an equation to get this. So step 1, guess an x value, and then find y from x, y plot. So that's step 1. So we can guess an x, right here, and then we can read up here and find out what our y value is. So that's step 1. Guess what the x value is. Step 2, plug x, y guess into equation 2. So that's our second step. Equation 2 is this one right here. That's just the material balance for the more volatile species. So what we'll do is we'll take our values that we've guessed for x and y and plug them into this equation. Step 3, we evaluate left-hand side of 2 and whether it's equal to the right-hand side of 2. So if we've gone through and evaluated that, so we plug in the numbers that we've guessed for x and y, and if the answer is yes, we are done. We're good. If not, no, we're going to go ahead and guess an x and a y value. Another x and y combination, which we can again get from our vapor-liquid equilibrium plot and go from there. And that's the general procedure. We just keep guessing x's and y's until we get eventually to the point where all the solution is self-consistent and equation 2 works out. And so it's just a more or less a trial and error type approach. Now if we have equations for the vapor-liquid equilibrium data, so we might have equations like we've discussed in class, then we could use those equations in combination with our material balances. So we might take these material balance equations and vapor-liquid equilibrium equations that relate x to y, and then we just have all these algebraic equations that we use to solve for our unknowns. And that's how we would go about solving this. And there's another way which we'll use, and I'll explain in the near future, about using a graphical method to solve for it. So, but that's all I have to say about go ahead and solving for the flash drum for now.